in our previous sessions, we have already seen that the moment of inertia of any body, of any plane, such as this plane, with respect to the axis x and y, can be given as Ix is equal to integral of y square dA, and with respect to y-axis we can write it as Iy is equal to x square dA, where x and y are the perpendicular distance between this reference axis and this elemental area dA. And similarly, the product of inertia Ixy can be determined as integral xy dA, that is the perpendicular distance between x-axis and the perpendicular distance between y-axis multiplied by the area element. And for this entire area we need to integrate this. This is what we had seen last time. But along with this we had also seen that if I move this frame of reference to some other point away from away from the origin, or away from the centroid of this body, and then we had seen that as we shift this frame of reference, as we increase the distance between the newer frame of reference, as we increase this distance between newer frame of reference, our values of moment of inertia was changing. It was changing with by changing the distance. It was changing by changing the frame of reference. In this session we will see that even if we keep the origin same, but if we just rotate the frame of reference with some angle theta with respect to the previous frame of reference, still the value of moment of inertia and product of inertia will change. And that is what exactly we will see in this topic, rotation of axis. And then we will observe that as we are rotating this frame of reference by some angle, at particular some angle, the moment of inertia obtained for that particular frame of reference will be the maximum moment of inertia. And then the axis for which the moment of inertia which is obtained for this particular lamina is maximum are called as principal axis. So this is what we'll be looking at it today. So what I will do is first, so let us make ourselves clear that x is the perpendicular distance of this area element with respect to y-axis. Y is the perpendicular distance between this area element and x-axis. And then as I have transferred or rotated this frame of reference to the new axis x1 and y1 by angle theta, now the perpendicular distance has been changed to x1 and y1. Now x1 is the perpendicular distance between this area element dA and the new axis y1, and similarly y1 is the perpendicular distance between this area element dA and the new axis x1. Then further what I will do is I will drop one perpendicular right from this point on this new axis x1, and if I do that I will get something like this. I'll get something like this, right? So this is our perpendicular which I have dropped from right from this point on the x1 axis. So let us name this point. I will name this point as A, and then similarly I will name this point as B. I will name this point as, let us say we call this point as C here. This point is E, and then this point I will call as D. This point I will call as D. So what I need to find is, here I will try to establish some relation between x1, and then with this I will try to establish some relation between x1 with that of x and y, and similarly I will try to establish some relation of y1 with that of x and y. So here Here we can observe that x1 is nothing but it is equal to AB plus BC. Here x1, this entire x1 is AB plus BC. Now this AB is also equal to OD, right? This AB is also is equal to OD. Now since this angle is theta, even this angle should be equal to theta, right? And then even this angle should be equal to theta. Now since this angle is theta, and then since this is y, this length will be also y. So since this is y and this angle is theta, I can very well say that OD will be y sine of theta. This OD will be y sine of theta because this is y. This component will be y cos theta along with theta, and this component will be y sine theta. So OD is y sine theta. Then what is BC? What is BC? This is x, and this is theta. So the component along the theta will be x sine theta. So from here we get BC as x sine of theta. Then from this we get x1 as AB, which is OD, is y sine of theta, and then BC is x sine of theta. Now if we do the similar analysis, I can find y1 as y cos of theta minus x sine of theta, y cos of theta minus x sine of theta, because y1 is nothing but OA, which is equal to BD, which is equal to ED minus BD, and this DE is nothing but nothing but y cos of theta, and then this EB is x sine of theta. This BD will be this minus this, that is y cos of theta minus x sine of theta. So this y1 we get it as y cos of theta minus x sine of theta. So once we get this, then I can say that Ix1 Ix1 is nothing but the moment of inertia of this element or of this whole area with respect to x1, and that is nothing but integral of y1 square dA. But from this expression we get y1 as y cos of theta minus x sine of theta the whole square dA. Now if I expand this further, I should get this expansion, this will be integral of y square cos square theta plus x square sine square theta minus 2 times xy sine theta cos theta multiplied by dA. So further, if I do the simplification, I should get this as cos square theta integral of y square multiplied by dA, plus this term should be sine square theta into integral of x square dA, and then further this will be minus sine theta cos theta, and we have this 2 here, and then integral of xy dA. Then from here we know that y square dA is nothing but Ix. So this will be Ix cos square of theta. X square of dA, integral of x square of dA is nothing but Iy, that is the moment of inertia about y-axis. So this will be Iy sine square of theta. And then we have this as minus 2 times integral of xy dA is nothing but product of inertia about the axis x and y. So this will be 2 times I xy sine theta cos theta. So this is nothing but Ix1, that is the moment of inertia about the new axis x1. Then further I can use the trigonometric identities as cos square theta is nothing but 1 plus cos 2 theta divided by 2. Similarly, I have sine square theta as 1 minus is 1 minus cos 2 theta by 2. And then I can also use this trigonometric identity that sine 2 theta is nothing but 2 sine theta cos theta. Once we get this, I can further substitute it here, and I should get this Ix1 as Ix by 2 1 plus cos 2 theta, then Iy by 2, 1 minus cos 2 theta, and then this should be minus Ixy sine 2 theta. If I further simplify this here, I should get this as Ix plus Iy by 2 plus Ix minus Iy by 2 cos 2 theta minus Ixy sine 2 theta. So this is a very important expression which we have got now. This expression exactly tells us that what will be the moment of inertia about the new frame of reference x1 y1, and Ix1 will tell us what will be the moment of inertia about the axis x1. If I know the moment of inertia about the original x-axis, and if I know the moment of inertia about the original y-axis, and if I know the product of inertia with respect to the original x and y-axis, then I can find the moment of inertia about the new axis x1, provided I know the angle of rotation, that is theta, that is this angle theta. So this is what we get here. Now similarly, if I try to obtain what is Iy1, that is the moment of inertia about the new axis y1, then with the same analysis I can very well find that Iy1 will be equal to Ix plus Iy by 2 minus Ix minus Iy by 2 cos 2 theta plus Ixy sine 2 theta. We can try this derivation to derive this expression for Iy1. Only thing is, now you will have to consider this Iy1 as integral of x1 square dA, where you need to substitute x1 as y sine theta plus x sine theta, and if you do that and if you simplify it like this, you should be able to derive this expression for Iy1. I will call this expression as expression 1 and expression 2. So if I add them up, if I add these two expressions, expression 1 and expression 2, then I should get on the left hand side as Ix1 plus Iy1, and on the right hand side this two term will cancel out, this two term will cancel out, and then I will have this term and this term, and if I add them up I should get this as Ix plus Iy. And again, this is also a very important expression along with the above two expression, that, and what it tells us is the sum of moment of inertia about any axis will be always same. That is, if this was our original axis x and y, then the sum of moment of inertia about original x and y will be equal to the sum of moment of inertia about the transformed axis or the rotated axis x1 and y1. So we have here altogether three expressions, that is this expression, this is expression 1, a very important expression, and very important expression. So I have this one expression, I have this second expression, and then I have this third expression. So this is how we'll be able to find the moment of inertia about the new frame of reference x1 and y1. So as we rotate this frame of reference with different thetas, our value will go on changing. This x1 and y1 will depend upon what is the value of theta. If theta is 30, we'll have one value for ix1, one value for y1. If we say the change the angle to say 40, again this value will change, this value will change, but no matter what, the summation of these two values will be always equal to ix plus iy. Let us try to find now the product of inertia. The product of inertia about the original axis x and y is this. It is integral of x y dA, which we had already seen last time. But now the product of inertia I x1 y1 will be equal to x1 y1 dA. Earlier it was xy dA, but now since we have transformed the frame of reference or rotated the frame of reference by angle theta, the perpendicular distance has changed to x1 and y1. So the new product of inertia about the axis x1 and y1 will be x1 multiplied by y1 dA. But we know what is x1 and y1. x1 is y sine theta plus, I'm sorry, this should have been x cos theta. This should have been x cos theta. So this will be x cos of theta. This should be x cos of theta. So x1 is y sine theta plus x cos of theta. So this should be y sine of theta plus x cos of theta, that is x1, and similarly y1 will be y cos of theta minus x sine of theta, that is y cos of theta minus x sine of theta, and this is multiplied by dA. This is multiplied by dA. Now if I simplify this further, I will get this as, if I have to simplify this further, I will get this as integral of xy cos square theta dA, that is this multiplied by this is xy, x multiplied by y cos square theta times dA, this term dA. Then I will have this multiplied by this, that is minus integral of x square sine theta cos theta dA. Then I have this term that is plus integral of y square sine theta cos theta dA. This is the third term, and the last term will be minus integral of xy, sine square theta dA, sine square theta dA. Now if you see here carefully, this is integral of xy dA, which is nothing but ixy. It is nothing but ixy. So this will be ixy cos square theta. It will be ixy cos square theta, and then this last term will be minus ixy sine square of theta, and then this term here will be minus I y sine theta cos theta, and the last term, this term will be plus ix sine theta cos theta. Now if I group all this together, I should be able to write this as ix minus iy, that is this term, multiplied by sine theta cos theta, and then if I group this term together, it will be plus ixy cos square theta minus sine square theta. And again, if I use this trigonometric identities which I had used here, this trigonometric identities, I should get this as, finally I should get this as ix1 y1 should be equal to ix minus iy by 2 sine 2 theta plus ixy cos 2 theta. And again, this is a very important expression wherein this expression gives us the relation between the transformed product of inertia to that of the initial moment of inertia and the product of inertia. So this value for a given frame of reference, this value totally depends on this theta. As this value of theta will change, this product of inertia value will go on changing. So this is our fourth equation, a very important expression. So since we have got now all these four expressions, I can now very well use this expression to find what where exactly this value of moment of inertia will be maximum. We know that as we are changing this theta, these values will go on changing. So there will be some particular value of theta where the value of moment of inertia along that axis will be maximum, and that is what exactly we'll try to find now. So for that, what we will do is, so I basically want to know at what value of theta this value will be maximum. For that, what we do is, as you know, we will have to differentiate this equation with respect to theta, and we will have to equate it to 0 because I need to find the maximum value of this I for the value of theta. So what we will do is we'll differentiate this equation with respect to theta and equate it to 0, and we should be able to find the value of theta for which this value will be maximum. So that is nothing but we are trying to basically find the value of principal axis, or the value of moment of inertia along the principal axis. So we'll begin with that. We will differentiate this equation 1 with respect to theta. If I do that, this term will be 0. This term will be ix minus iy by 2 sine 2 theta, and the sign will be minus. So what I will get is d by d theta of ix1 will be, this term will be 0 because here there is no theta term. This term will be ix minus iy by 2, ix minus iy by 2, and this value cos 2 theta will be minus sine 2 theta, minus 2 times sine 2 theta. And then this term similarly it will be minus ixy minus ixy cos 2 theta, and of course this 2 will be there by chain rule, and this should be equal to 0. In that case, I get this as ix minus iy sine 2 theta plus 2 times ixy cos 2 theta is equal to 0. And then further if I simplify this, I should get this as tan 2 theta is equal to minus 2 times ixy divided by ix minus iy. So this is the angle of theta. This is the angle of theta where the value of moment of inertia will be maximum. So I can call this as theta p to indicate that this is the value of theta of the principal angle. This is the theta value of this principal angle. So basically this expression will give us the the orientation of principal axis, and I will mark this equation as equation 5, again a very important equation. So this is the value of theta basically, where the value of moment of inertia will be maximum, and that axis will be called as principal axis. If I try to plot this angle, then what I can do is I can draw one right angle triangle. Here, and if suppose say this angle is 2 theta p, then we have tan of 2 theta p as minus 2 ix divided by ix minus iy. So tan to theta p is nothing but opposite by adjacent. So in opposite I have minus ixy, and for adjacent I have ix minus iy by 2, right? So with this again, if I say tan 2 theta p, it will be minus ixy divided by ix minus iy by 2. So I get back this expression. If this is the case, then this will be the resultant r, and resultant r can be found out as by Pythagoras theorem. R square will be this term square, ix minus iy by 2 the whole square, plus it should be ixy square plus ixy square. So from this I get this r as, I'm running out of space, I'll write it here. I get r as plus or minus root of ix minus iy by 2 whole square plus ixy square. So this is what we get, this r as plus or minus root of ix minus iy by 2 whole square plus ixy square. So this is the resultant. So if I again look at this figure carefully, then I get sine 2 theta p, sine of 2 theta p, I'll write it here. Sine of 2 theta p is nothing but opposite by hypotenuse, that is minus ixy divided by r, whereas cos of 2 theta p will be adjacent by hypotenuse, that is ix minus iy divided by 2 times r. So this is what we get, sine 2 theta p and cos 2 theta p. So what we will do is, so these are basically the angles where I will get the maximum value of ix1. So if I use this now angles in this expression, that is the value of theta, where the value of moment of inertia will be maximum, I will get this as the maximum value. So if I do that, if I substitute the value of sine 2 theta p and cos 2 theta p in this expression, I will get this as ix1 equal to, or in place of ix1 I will call that as I1 now. I1 will be equal to, let me remind you again that I have the two values of r here, one is plus and one is minus. So initially I will consider the plus value of r. In that case I will get I1 as ix plus iy by 2 plus root of ix minus iy by 2 whole square plus ixy square. And similarly the value of I2 will be, now I2 will be, again what we will do is we'll substitute the value of sine 2 theta p and cos 2 theta p in the same expression. In this expression here I will put the value of sine 2 theta p, here I will put the value of sine cos 2 theta p, here I'll put the value of sine 2 theta p, but this time I will consider this r as minus. In that case I will get this now I2 value as ix plus iy by 2 minus root of the same term ix minus iy by 2 the whole square plus ixy square. And then we can write this values as, we can finally write this value as I1 comma 2 is equal to ix plus iy by 2 plus or minus root of this term ix minus iy by 2 the whole square plus plus ixy square. These equations might look very familiar to you, wherein you all had solved the problems of principal stresses. So it is similar to that. These are the maximum values of moment of inertia for this value of theta. So basically what we have seen here is, as we will rotate this frame of reference x and y axis by some angle, the moment of inertia and the product of inertia with respect to this new axis will be different to that of the original frame of reference, and as we are rotating this frame of reference there will be some value of theta somewhere. So at present it is theta. So if I take a new frame of reference like this, so this will be some different theta. So as I am rotating this at some value of theta, we will see that these values of moment of inertia will be maximum, and those axes where the values of moment of inertia will be maximum are called as principal axis, and that theta is called as the angle of principal axis or orientation of principal axis. So along with this equation 5, this is the equation 6, which is again very important.